Good day, everyone. I'm Jessa Elano Bersanas from BSE-2J. Today, me and my group mates will be discussing about the lesson 12, the endogenic processes. But before we begin, let us first read the objectives, because this will serve as our guide as we go through on our lesson. This will serve as our scientific target. Okay, first, we will explain why the Earth's interior is hot. Then, we will describe how magma is formed. We will demonstrate what happens after magma is formed. And lastly, we will discuss the three main endogenic processes. So everyone, let us take a look at this scientific overview. Endogenic processes takes place within the earth but are responsible for the changes on the surface of the planet. These changes may include volcanic activity, tectonic plate movements, crustal deformation, isostatic adjustments, and magmatic intrusions. In magmatic intrusions includes silts, which form when magma intrudes between the rock layers, forming a horizontal or gently dipping sheet of igneous rock. Another one, the dikes, form when magma pushes up towards the surface through cracks in the rock. Dikes are vertical or stiffly dipping sheets of igneous rocks. Then lastly, the batholiths. These are a large, deep-seated intrusions, sometimes called plutons, that form as thick, viscous magma slowly makes its way towards the surface but seldom gets there. Studying these processes help us clearly understand why Earth's appearance has been undergoing constant remodeling. Let's come now to source of energy. Again, endogenic processes takes place within the Earth but are responsible for the changes on the surface of the planet. Source of energy of endogenous geological processes is from within the Earth itself. What do you think is the ultimate source of energy for these processes? You're right. Internal heat of the Earth. The internal heat of the Earth is the main power source of the endogenous processes that shape the planet's surface from within. Meaning that the source of energy for these processes arises internally from the Earth. So imagine if we lost this internal heat, there might not have an endogenous geological processes that can occur because, again, it is a source of energy. With regards to the internal heat of the Earth, as part of it, what we have is the leftover heat, called the primordial heat. From the formation of our planet about 4.5 billion years ago, this is an accumulated heat release or formed during the early stages of the Earth's formation. This leftover internal heat is still being dissipated to the surface of our planet as part of the Earth's cooling down processes from how it was billions of years ago. When we say dissipating to the surface, this is the process of this internal heat being gradually released and dispersed from the Earth's interior towards the surface, meaning from the underground heat going to the top, which is the surface. Otherwise, since this primordial maintains the habitable condition of the Earth, we would not be able to survive on it. If there will be no or without this ongoing dissipation of the Earth's internal heat, the planet would become frozen, lifeless world like it is inhabitable. This primordial heat is critical factor that makes the Earth a suitable environment for life to thrive. But why does the Earth not cool down completely? The Earth has attained a stable temperature because it also continues to generate heat as fast as it is losing it. Other source of Earth's internal heat. We have radioactive decay of natural radioactive elements like U-238, U-235, TH-232, and K40 in the Earth's lithosphere from mantle and crust. This second type of heat is called radioactive heat. Many rocks in the crust and in the interior underground radioactive decay, the decay produces subatomic particles that move through the earth and their energy of motion is converted into heat energy. It is estimated that the core of our planet is about 5,000 to 7,000 degrees Celsius and is as hot as the surface of the sun. Okay, trivia. One of the reasons why Earth is still dynamic while Mars is not anymore is the difference in the internal heat of the planets. Earth has substantial internal heat. This pertains to the significant amount of thermal energy present within the planet's interior, which is necessary in sustaining the dynamic and life-supporting environment on the Earth's surface, while Mars has relatively low internal heat flow, meaning this is one of the reasons why Mars does not support life at least on the surface. The internal heat of the Earth flows towards the surface and powers the endogenous processes. The picture below shows the internal structure of the Earth and contribution of each layer to the overall heat flow in the entire globe. The entire core contributes about 22%, the lower mantle 32%, the upper mantle 22%, and the crust 24%. As to how heat flows or heat transfers, conduction is the mode from the inner to outer core. Since the inner core is solid, in the outer core it is convection since it is liquid. In the lower and upper mantle, the process is convection. At the surface, the process is advection, although the arrows indicate an upward or vertical direction. The energy will be transferred or dissipated at the surface in a generally horizontal direction due to the action of, say, the wind or the atmosphere or ocean currents. It is estimated that both primordial heat and radiogenic heat contribute more or less equally to the total internal heat of the Earth. As the internal heat of the planet reaches the surface, the areas or places where they come out in greater amount would be in plate boundaries as how in the image. The red portions are hotter areas. These are the mid-oceanic ridges and oceanic crust. These are places where the Earth's internal heat comes out the most and are therefore active areas of endogenous processes. Now, let's come now to the types of endogenic processes, and there are three, which is the folding, faulting, volcanism. The following members of this topic, endogenic processes, will be the one to continue this discussion. Again, I'm Jessa Ilano Barsanas. I hope you have learned something. Thank you.
So good day everyone. I will be continuing the discussion about our topic in lesson 12. So the topic that I will discuss is all about the formation of magma. So I am Gavino Ibes Jr. from BSE-2J, a science major. The first important effect of the internal heat of the planet is the formation of magma. So when we say Earth's internal heat, this heat have resulted in the existence of different processes happening in our planet. One of these is the magma formations. So next po. So formation of magma. Magma is composed of the minerals contained in the source rocks, some unmelted minerals as well as gases like water vapor, carbon dioxide, or hydrogen sulfide. So when rocks melt due to the heat from an adequate source such as the internal heat of the earth, the magma will form, and it is also called melt. So the temperature of magma ranges from 700 to 1300 degrees Celsius. It must be very hot for the rocks to melt. Next po. Magma is composed of molten or partially molten rock which is stored under Earth's surface. Magma is extremely hot liquid and semi-liquid rock located under Earth's surface, and Earth has a layered structure that consists of the inner core, outer core, mantle, and crust. Much of the planet's mantle consists of magma. This magma can push through holes or cracks in the crust, causing a volcanic eruptions. So, the word magma is a Greek word which originally meant thick ointment. When magma finds its way on the Earth's surface, it changes its name to lava. So, it plays a crucial role in the formation of igneous rocks and volcanic landforms. So, next po. Where does magma form? Magma forms from rocks melted in the lithosphere, crust, upper mantle, asthenosphere, so magma is below the surface of the Earth. So magma forms in various geological settings where conditions allow for the potential melting of rocks in the Earth's mantle or crust. So next po. Why does the melting temperature of rocks vary? It all depends on the melting point of the minerals that make up the rock. Low melting point minerals naturally melt first. Rocks melt at depths of between 50 to 100 km below the surface. So, the melting temperature of rocks varies due to a combination of their mineral composition, the presence of volatiles, the pressure conditions they are under, and the amount of heat transfer from other sources, and the interaction between different minerals. So magma does not form in volcanoes. It is where they came out, having been formed way below the surface of the planet. Rocks melt at depths of between 50 to 100 kilometers below the surface. The planet gets hotter as one goes deeper at 25 degrees per kilometer deep. This is called as the thermal gradient. So that process is called the thermal gradient. So now there are two processes in magma formation. The first one is the compression melting, and the second one is the flux melting. So when we say decompression melting, it's the process of creating magma by reducing the pressure at the constant temperature. Decompression melting occurs when pressure on hot mantle rock is reduced as it rises towards the Earth's surface. As the rock ascends, the drop in pressure lowers the melting point at the minerals, leading to partial melting. So, flux melting occurs upon the introduction of volatiles, which breaks the chemical bond in rocks, at the same time lowers the melting temperature of rocks. So, flux melting occurs when volatiles such as water and carbon dioxide are added to the mantle or crustal rocks. These volatiles lower the melting temperature of the rocks. Commonly takes place in the subduction zones where oceanic plates carry water-rich sediments into the mantle. Next po. So now this is the diagram that we will discuss further. So magma formation is commonly in the following location: the rift valleys, oceanic or mid-oceanic ridges, the hot spots or mantle plumes, and the subduction zone. So this will be the rift valleys, the mantle plumes, the oceanic ridges, mid-oceanic ridges, and the subduction zone. And this will be another subduction zone. So, in rift valleys, continental rifting can lead to the thinning of the lithosphere and upwelling of the asthenosphere, carrying a decompression melting. So, in rift valleys, there will be a decompression melting. The presence of melting here, the process of melting here is the decompression melting, where it can lead to thinning of the lithosphere and upwelling of the asthenosphere, so that decompression melting is occur. So the second one is the mid-ocean ridges. The mid-ocean ridges are in decompression melting also. So mid-oceanic ridges or oceanic ridges is when tectonic plates are diverging, mantle material rises to fill the gap. As it ascends, the pressure decreases, leads to melting. So in this mid-oceanic ridges, when plate tectonics are in, the two plate boundaries are separating to each other, that makes it the magma fill in the gap between the two plates that are separating to each other. So that it ascends, the pressure decreases, leading to its melting. So the third one is all about the hot spot or the mantle plumes. Here in hot spot or mantle plumes, the melting processes that are present here is all about the compression decompression melting. So hot buoyant plumes of mantle material rises from deep within the earth. When the plumes reach shallow depths, decompression melting is occur. So when the hot spot or the mantle plumes reach the shallow depths of the shallow depths, it leads to decompression melting, wherein decompression melting is occur when pressure on hot mantle rock is reduced as it rises towards the earth surface. So now, the last one is the subduction zone. So here in the subduction zone is the melting processes that are present here is the flux melting processes. So in subduction zone, as an oceanic plate subduct beneath a continental or another oceanic plate, it comes water and other volatiles into the mantle. The addition of these volatiles lower the melting point of the mantle rocks, resulting into magma formation. That's why magma formation are present when the tectonic plates are present too. So there are different tectonic plates, the divergent boundary, the convergent boundary, and the transform boundary, wherein those plate boundaries resulted to magma formation and the magma rise up to the earth's surface. So that would be all my topic about the formation of magma. So I am Gabino Ibis Lombre Jr., your reporter. Thank you for listening.
Hello everyone, I am Divina Rica Boquiña from BSE-2J and I'm going to discuss mantle convection, seafloor spreading, and continental drift. We all know that convection is a heat transfer movement that occurs in fluids like liquids or gas due to temperature differences. For example, in boiling water, the water near the heat source is heated, then rises to the top, cools at the surface, and sinks to the bottom. It is because when the water is heated at the bottom of the beaker, the molecules near the heat source gain energy, become less dense, and rise to the top. As these hot molecules reach the surface, they release heat to the surroundings, cool down, become denser, and then sinks back to the bottom. This process is then repeated, creating a cycle known as convection currents. Scientists hypothesize that convection also happens in the Earth's mantle. The mantle is mostly solid rock, but it can flow slowly over long periods of time due to the heat of the outer core. This heat causes the rock in the mantle to become hot and less dense, leading to the rise of hot material towards the Earth's surface. As this hot material reaches the top of the mantle, it releases heat to the cooler surroundings, making it denser, and then it sinks back towards the core to complete the convection cycle. In the process, a cycle or current is created. Thus, the mantle undergoes convection current as a form of the heat flow in the Earth's internal heat. The rising and sinking of the material in the mantle create forces that push and pull the tectonic plates, leading to seafloor spreading and continental drift. So, what is seafloor spreading? Seafloor spreading is the process by which molten material adds a new oceanic crust to the ocean floor. In the 1960s, geologist Harry Hess proposed that the seafloor was moving outward from the mid-oceanic ridges caused by the convection currents in the mantle. This creates a new seafloor which then spreads away from the ridge in the both directions. The youngest oceanic crust is formed at the crest of a mid-oceanic ridge, and the crust becomes progressively older away from the ridge. The oldest oceanic crust is then subducted and reassimilated in the mantle. The Mid-Atlantic Ridge is a prime example of seafloor spreading. It is a divergent plate boundary located in the middle of the Atlantic Ocean. The Mid-Atlantic Ridge stretches from the Arctic Ocean in the north to the Southern Ocean in the south and is one of the longest mountain ranges on Earth. It separates the Eurasian Plate and North American Plate in the North Atlantic, and the African Plate from the South American Plate, creating a rift where a new oceanic crust is formed through volcanic activity. Magma rises from the mantle to the surface, solidifies, and adds a new material to the ocean floor. This process of seafloor spreading results in the continuous widening of the Atlantic Ocean. Harry Hess' discovery of seafloor spreading confirms Alfred Wegener's continental drift theory. Continental drift theory is the movement of Earth's continents relative to each other, thus appearing to drift across the ocean bed. Alfred Wegener hypothesized that all of the modern-day continents had previously been clumped together in a supercontinent he called Pangaea, from ancient Greek meaning all lands or all the earth. Pangaea existed about 240 million years ago. By about 200 million years ago, the supercontinent began breaking up. Over millions of years, Pangaea separated into pieces that moved away from one another. These pieces slowly assumed their positions as the continent we recognize today. Scientists initially rejected Wegener's theory of continental drift he published in the early 20th century because it was lacking the mechanism for how it works. Why did the continents drift, and what patterns did they follow? But now, it is widely accepted due to the further development of the theory of plate tectonics. Thank you so much for listening. I hope you learned something today.
Hi, my name is Meros Bihalyare. Welcome to the real world of Earth science. This surface of Earth is really amazing, and for years scientists have been finding answers to questions like how did mountains become so tall, and what makes some valleys deeper than others. And they've given to us answer that what this video is all about endogenic process. Scientists believe that one time all the land on Earth was joined together as one big land mass is called a continent. Millions and millions ago began to break apart. Every continent has a wide variety of landforms. A landform is any natural formation of rock and dirt that is found on Earth. Different forces on Earth are constantly at work in changing all landforms. Some forces come deep within the Earth to develop some land formations. Other landforms created in shape by the action of winds, water, and ice on Earth's surface. Highland formation mountains are Earth's largest land formation. Mountains are found everywhere on Earth. Mountains are made of rock and land. Some mountains stand alone and are surrounded by lower land. Other mountains are part of a group of mountains called a mountain range. The main endogenic, we have the three different types of mountains. We have folding, faulting, and volcanism. The best explain how mountain valley and other surface features are made. You need to understand that the earth is made of the different layers, a solid core and a center liquid outer core, and then a mantle of heavy rock which is partially liquid. The part that we live is on the crust is plates. Take a look these pictures. We're showing the rocks folding as a result of very strong forces. Folds can be microscopic or can be macroscopic. The folding of rocks layers can form mountain, valley, and other surface. Fold mountain develops from large-scale folding of a crust along plate boundaries, and landforms from folding are some of the proponents. One in the world like the Himalayas from Asia, the Andes from South America, and the Alps from Australia. One example fold mounting, the mechanism for folding and the rocks layers will be fully discussed in the next lesson. Hola, it's time to review.
So we have here the faulting processes, one of the main endogenic processes. So faulting is a process of causing fracture, breaks, or cracks in rocks or rock layers due to shear forces applied that overcome the forces that hold them together and where movements has occurred on either side of the fracture. So, as its core, the faulting process refers to a geological phenomenon. It is what happens when the Earth's crust breaks due to physical forces leading to the movement of large blocks of crust. This process is fundamental in shaping the Earth's surface. Nagki-create na ito ng features like mountains, valleys, and pwede din mag-create or mag-cause ng earthquakes. So, next is fault plane. The break or crack is called fault plane. So, it is the outer layer within the earth that moves during an earthquake. So, it's where two pieces of the earth's crust have slipped through each other. So, these movements may be vertical or horizontal. So we have here the San Andreas Fault. So the San Andreas Fault is formed about 30 million years ago as the North American plate engulfed nearly all of the Farallon plate. Since then, the North American plate has ground against the Pacific plate um, at a boundary called a strike-slip fault. So, Marikina Valley Fault System is also known as the Valley Fault System. So, this fault is due to move within about 50 years and it is also a strike-slip fault. So, it is a dominantly right lateral, yun nga, strike-slip fault system in Luzon. So, it extends from Doña Remedios Trinidad, Bulacan in the north and runs through the provinces of Rizal and the Metro Manila cities of Quezon, Marikina, Pasig, Taguig, and also the Muntinlupa. And the provinces of Cavite and Laguna that ends in Canlubang. So, kung makikita nyo po yung red line, yan po yung valley fault system. So, faults where the tectonic plates of the earth collide, separate, or slide against each other. Kapag ang faults ay gumalaw, tremendous amounts of energy are released during or nagkukos ng earthquakes. So, yun po, as we go on to the lesson, we will encounter the three basic categories of faults, yung normal fault, reverse or thrust fault, and also yung transform or strike slip fault.
And now the next topic is all about types of fault. In this topic, we have four types to discuss. The first one is the strike-slip fault. It is a horizontal or vertical fault motion. When the rock here on either side of the fault line move horizontally in opposite direction past each other, the rocks are divided into two, the far side and the here side, depending upon to your reference point. Strike-slip fault is one in which the two blocks of rock slide past one another. A strike-slip fault is called by a build-up of stress that is released when two rocks slide past one another. This stress is known as shearing stress, which is a type of stress that is parallel surface, such as two blocks of rock in the strike-slip surface. Strike-slip faults can be classified into two ways: left lateral strike-slip faults or right lateral strike-slip faults. This classification depends on the perspective of the viewer and the motion of the two blocks of rocks. For example, if an observer is standing on one side of the strike-slip fault and the block of rock opposite the observer is moving to the left, the fault is considered a left lateral strike-slip fault. This motion is also known as sinetral strike-slip fault. If the block of rock opposite the observer moves to the right, it is considered a right lateral strike-slip fault. This motion is also known as dextral strike-slip fault. The second type of fault is the normal fault. It is a vertical motion. The rocks at either side of the fault line are divided into footwall or underlying block and hanging wall or overlying block. In the normal fault motion, the hanging wall moves downward while the footwall moves upward. As the arrows indicate, this became the closed here is being pulled apart. A deep slip fault in which the block above the fault has moved downward relative to the block. This type of faulting occurs in response to extension and it is often observed in the western United States basin and range province and along oceanic range systems. This fault motion is caused by tensional focuses and result in extension. Normal faults result from tensional forces when rocks are displaced away from each other. The third type of fault is a reverse fault or thrust fault. It is also a vertical fault motion. When the rock moves in a reverse direction compared to the normal fault, this time the hanging wall moves upward while the footwall moves downward. There, the crust is compressed from both ends. In a reverse fault, the block above the fault moves up relative to the block below the fault. This fault motion is caused by compressional forces and results in shortening. A reverse fault is also called thrust fault if the dip of the fault is plane is small. The last type of fault is the oblique slip fault. It is a both vertical and horizontal fault motion. When the rock in this type of fault is exhibit both vertical and horizontal movements, the hanging wall has dropped down and moved to horizontally to the right while the footwall has moved upward and also horizontal to the left. Both tension and shear forces are at work here. Nearly all faults will have same component of both normal or reverse. So defining a fault as oblique requires both deep and stripe components to be measurable and significant.
Good day everyone, I am Jubel C. Palmiano from BSE-2J. I will be discussing about the third type of endogenic processes, which is volcanism. What is a volcano? Volcanoes are opening in the Earth's crust through which molten rocks, gas, other materials are released from the deep within the Earth. Also, volcanoes are formed when molten rock called magma rises to the surface. The magma can come from the Earth's mantle or from subduction zone when one tectonic plate slides beneath another. So, where on Earth can we find volcanoes? Mostly found along the boundaries between tectonic plates, where the movement of the lithosphere causes intense heat and pressures. Volcano may also form a hotspot areas away from the plate boundaries where magma breaks through the lithosphere and erupts. So here are some famous volcanoes, which is Mount Fuji from Japan and Acatenango from Guatemala and White Island from New Zealand and Mount Sinabung from Indonesia. Volcanism. Volcanism is a phenomenon or a situation whereby the eruption of the molten rock magma onto the surface of the earth. These are the process of volcanism. The process of volcanism starts from the eruption of the molten magma from the mantle or the lower crust to the outer crust. When we say magma, it is a molten rock, a mixture of liquid rock minerals and dissolved gases. It is formed by the melting of the Earth's mantle. Magma forms when the rock reaches temperature high enough to melt them. Most rocks begin to melt at temperature between 800 to 1200 degrees Celsius. Let's now watch the introduction of volcanoes. Volcanic eruption can be dangerous, but with proper preparation, we can stay safe. Here's how. Stay informed. Pay attention to officials' warning, updates, and evacuation order from local authorities. Emergency plan. Create a family emergency plan that includes meeting points, communication methods, and designated emergency kit. Emergency kit. Prepare a kit with essential items like food, water, first aid supplies, flashlights, and batteries. Evacuation routes. Familiarize yourself with evacuation routes and practice evacuation drills with your family. And that's all. Thank you for listening.